Inventor of this mathematical tool called as Fourier series is Jean-Baptiste Joseph Fourier, who lived between 1768 to 1830, and he was a French mathematician who has contributed this very popular and important tool to us. Now, Fourier series is basically a type of signal representation. So various type of representations we come to see here while studying the engineering subjects here, and every type of the signal representation has the characteristic features. So many a times few of the representations are quite convenient to get the understanding and to process the things in better manner here. So we shall definitely see the things with respect to the Fourier series, which is one of such a type of signal representation here. Now in this type of signal representation by Fourier series, there are the decomposition representations for the signal into the use, and these are basically of the sinusoidal type here. The sinusoidal nature is repetitive nature. As we start from the zero level, we can go up to the positive maxima with the gradual increase, come back to zero into the same gradual decreasing manner. The same we repeat onto the negative side of amplitude as well. So that completes one cycle, what we can say about a sinusoid here. So the repetition of it gives us the sinusoidal signal here. So it may be a sine wave, it may be a cosine wave. So now these sinusoidals basically are nothing but the periodic signals here. So for the periodic signals, if such a decomposition is represented, this is nothing but the Fourier series, as it has been invented by the Jean-Baptiste Joseph Fourier. Now, with the help of the Fourier series, as we have the signals most possibly represented graphically to see the periodic nature, the sinusoidal nature, onto the horizontal axis, we either denote a parameter for measurement of the space or the measurement of time. So for measurement of time, we represent that particular signal amplitude versus the time instances, that is the time domain representation. With the help of the Fourier series, the representation of the same kind of information is to be made with the help of frequency components. Hence, we call it to be a signal represented into the frequency domain here. So now, as it is very clear that with the help of Fourier tool here, Fourier series, we switch from the spatial domain or the time domain to that of the frequency domain. It is very necessary to understand how exactly the same information can be represented. So for that purpose, there it is the simple example with the help of the Newton's experiment that he had conducted in the year 1672. So here the first experiment, the first part of this experiment, we can call it to be the analysis of the white light. So hereupon you can see the illustration where we have the incidence of white light from the left hand side to a glass prism kept at the center here. So upon having the white light, here it is mentioned a beam of sunlight, when it is incident onto the left hand side wall of this particular glass prism, onto the another hand we have the frequency components separated from this white light, and those are with respect to the white, the violet here, next to that the blue component, green component, yellow component, orange component, and a red component here. So the same white light that it was, it has been represented in terms of its components as listed here. So here each color that has been represented onto this right hand side correspond to a specific frequency range, or we can also come to see a specific wavelength range in terms of nanometers here. So right from the left hand side where we have the input as white light, to obtain the violet, blue, green, yellow, orange and red components, this is basically the analysis. So as we have the light signal here, white light here, this is analysis of the light into the colors. So this is the frequency analysis, as these colors correspond to the various frequency values here. So this is one part of the experiment here. The information is the same, but the ways of representations are different here. Now into the second part of the same experiment, we have the synthesis part of the white light here. So now we consider that with the help of first prism we have the frequency components, the different colors that have been extracted from the white light we have just now seen here. Now here we can make the use of another prism. The another prism has been positioned in inverted manner with respect to the earlier one, and whatever the spectral components we had obtained after passing the white light through this first glass prism, those have been fed as input to the another prism with the inverted position here. So on to the another hand, we come to obtain the white light that has been formed from all these components. So to look at this particular procedure, whereas all the spectral components combine to form the white light, again we can say this is nothing but the synthesis of the white light here. So with the help of this Newton's experiment, it is quite very clear that the representation of the information into the two forms, either into the white light or into its spectral components representing the different colors there, we can have. Now what is the importance of having such shifting of the representation type? It is nothing but the importance of the Fourier tool. Here we have the Fourier series here. So this signal decomposition become important while we have the analysis of LTI systems. So LTI standing for the linear time invariant system. Those we are dealing right from the study of signals and system subject before learning to this digital signal processing, advanced digital signal processing. Now there lies two important reasons why this Fourier series is very important with respect to the analysis of linear time invariant systems. The first reason lies that if we have the linear time invariant system and try to operate it by feeding certain kind of input to it, so that whatever the output, what we call the response of the linear time invariant system to this particular case, if the input is of the sinusoidal type, then the sinusoid of the same frequency but having the different amplitude level and the phase value is generated by such LTI system. Now another reason of having the Fourier series to be much more important to this LTI system is the linearity property of the LTI system also. Now here a linear summation of the sinusoidal components at the input produces the similar linear sum of the sinusoidal components at the output, hence we call it to be linear. Now this differs only into the values of the amplitude levels and the phase values from the input sinusoids here. Now in continuation to these two reasons for the importance of Fourier series to LTI system, as we see many another decomposition signals are also made possible, only the class of the sinusoidal and the complex exponential signals possess this desirable property in passing through an LTI system. Hence the Fourier series becomes very important concerning the LTI system analysis here. Now as in the starting of this particular chapter we have seen the differences between the continuous time signal, discrete time signal and finally the digital signal, we first of all see the details of the Fourier series when operated for the continuous time type of the signal here. And as we have the sinusoids here, basically this Fourier series is for the periodic type of the signals here. So here the periodic signal examples can be listed as the square waves, rectangular waves, the triangular waves, the sinusoids, and the complex exponentials here. Now let us discuss a brief with respect to what exactly the periodic signals we have here. So here we have the linear combination of the harmonically related complex exponentials. The mathematical representation of the same, we can give it with the help of this expression. So here we have the representation x of t. So as within the parenthesis we mentioned t here, this is the time domain representation. The signal amplitude can be denoted by x here. So it can be expressed into the form where we carry out the summation for the index vector k is equal to minus infinity to infinity operated over c sub x k in multiplication to the exponential e to the power j times 2 pi k capital F0 into t here. So now in this particular representation, the important is capital F0 here. So capital F0 can be obtained by taking the inverse of the fundamental time period. So in general, the fundamental time period can be denoted as capital T sub x p here, and it is again in the reverse way the inverse of this fundamental frequency component F0 here. Now here the F0 is a part of the exponential here. The exponential represented e to the power j times 2 pi k F0 t, where the k value holds the form 0 plus minus 1 plus minus 2 and so on. There are we having these exponential signals as the basic building blocks of this particular Fourier series from which the periodic signals can be constructed here. So this statement is very important. Into the mathematical transformations, the building blocks are most of the time the orthogonal components or the bases. These are the various terms we refer to. So for every such a transforming mathematical tool, we have these important bases here, and for the case of Fourier series, we have these nothing but the exponential components or exponential signals we can see here. Now with respect to the first equation that we have for x of t here, in order to have determination of the expression for the complex coefficients here that we have represented by c sub x k, we can have the multiplication on both of the sides by the complex exponential as represented. We have e to the power minus j times 2 pi capital F0 L t here. Now next to that we can carry out the integration on both of these sides, that it is left hand side and right hand side after the above process to the equation number 1 here, and here the resulting equation for the single period, if we have the integration mathematically, if we obtain it to form, we have the integral here we represent small t0 to t0 plus tp the time period. This is over the multiplication of x of t with the exponential e to the power minus j 2 pi l capital F0 t dt for the integration here. This is expressed as the integral sign represented the same, dt represented the same, we have the exponential represented the same here, whereas x of t can be represented the summation k is equal to minus infinity to infinity ck into e to the power positive j into 2 pi l f0 t here. Now in this representation onto the right hand side, we have the integral as well as the summation operations here. So summation operations we most of all prefer into the discrete cases here, whereas into the continuous cases we prefer the integration here. Now here if we have the interchange of the order of the summation with that of the integration, and then if we can have the combination of the two exponential, so that time the resulting mathematical expression gives a new form. So this new form here it is. We have the summation k is equal to minus infinity to infinity first of all taken. Then we have ck. Then the integral from t0 to t0 added by tp. Here we have the exponential e to the power minus j 2 pi capital F0 in the bracket k minus lt dt here. So here we represent into the simplest form the summation as it is ck. Next to that we have the ratio where we have the application of the lower and the upper thresholds of the integrals here. So here we have represented the exponential e to the power minus j 2 pi f0 k minus l into t divided by j times 2 pi capital F0 k minus l here. So the upper and the lower limits have been operated here, and if we keep k is equal to l, this is supposed to result into the zero value, and if we have k is equal to l, so for the first case the zero is resulted when they are not equal, and when they are equal we can have its reduced form into the integral t0 to t0 added by tp dt. This is equal to small t, and it has been operated by these two upper and lower integral limits here t0 to t0 added by tp. Finally it is resulting into the tp here. Now next to that, because of this particular things, the resulting equation gets to the reduced form that we see here. So into the reduced form we have the integral t0 to t0 plus tp operated over x of t into e to the power minus j 2 pi l f0 t dt. So this we can represent as c suffix small l in multiplication to the time period tp here. Now the Fourier coefficients in terms of the given periodic signal becomes of the form. Here we have the representation for CL. So in terms of first of all the time period 1 upon Tp, then the integral T0 to T0 added by Tp operated over x of t into e to the power minus j 2 pi l f0 t dt here. So by the next step we get it to the form 1 upon Tp integral over the time period in general Tp x of t multiplied by e to the power minus j 2 pi l f0 t dt here. Now for the application of the Fourier series representation for this periodic type of the signal holding true here for the continuous type, there are three conditions to get satisfied, and these are called as the Dirichlet conditions here. So one by one we shall see what are these Dirichlet conditions here. So the first condition is when a continuous time signal represented x of t has a finite number of discontinuities in any period, we can apply the Fourier series representation to it. The next condition is that the signal that we have represented as like x of t continuous time here, if it contains a finite number of the maxima and the minima during any single period, so that time also we can have the application of the Fourier series representation to it. Then at last we have the another important condition to get satisfied, that it is the signal x of t is absolutely integrable in any period. So this condition can be mathematically shown as the integral for the time period Tp operated over the mod of x of t, the input continuous time signal here of the time domain into dt. So this should be less than infinity, so it is supposed to obtain the absolute, that is the finite integrable value here. So with these Dirichlet conditions we complete the understanding of the Fourier series for the continuous time periodic signal here. Now as our subject is advanced digital signal processing, we have to definitely switch from the continuous time signal representation to first of all the discrete time representation here. So let us see what are the details of Fourier series for the case of discrete time periodic signals here. So here we consider that the input signal that generally we represent x of small n here is a periodic type of the signal where capital N can represent the time period into the discrete domain here. Now the Fourier series representation for such a periodic signal x of n will be consisting of the capital N, that is the period that we have here, the capital N number of the harmonically related the exponential functions. Those can be mathematically represented here as e to the power j times 2 pi small k into small n divided by capital N here, where small k holds the values 0, 1, 2, 3 up to capital N minus 1 here. And the Fourier series representation for the discrete time periodic signal can be given by this expression. Now the change as we switch from the earlier part to this part is very essential. In the earlier part, here onto the left hand side we had x of t here to represent the time domain representation in continuous form. Here as we have x of n, so n is for the discrete time representation here. So x of n is equal to the summation small k is equal to 0 to capital N minus 1 operated over ck multiplied to e to the power j times 2 pi k small n by capital N here. Now in this representation onto the right hand side, what we have, small c suffix k. So this is nothing but the coefficient representation in the series representation for the Fourier series case here. Now in order to have the derivation of the expression for these Fourier coefficients, we can have the use of following mathematical expression. So here we have the summation small n is equal to 0 to capital N minus 1 operated over the exponential e to the power j times 2 pi small k into small n divided by capital N, opting the value capital N when we have k is equal to 0 plus minus capital N plus minus twice capital N, and in the same manner. Otherwise we opt this RHS value to be equal to 0 here. Now next to this, as we find the representation in the above equation very similar to the case that we have discussed for Fourier series for the continuous time periodic signal, there the application of the geometric summation formula we see here, where we find the summation n is equal to 0 to capital N minus 1 for a to the power n is equal to opting the value small n capital N for small a is equal to 1, and when small a is not equal to 1 we have 1 minus a to the power capital N divided by 1 minus a here. Now to the earlier representation for the discrete time representation x of n with the help of the Fourier series here, if we have the multiplication on both of the sides by the exponential e to the power minus j 2 pi l into n divided by capital N, and finally having the summation of the product from small n is equal to 0 to capital N minus 1, we have this mathematical expression here. So in this mathematical expression you can see here this x of n has been multiplied by this exponential, so e to the power minus j 2 pi small l small n by capital N here, and then the summation here. So this summation is from n is equal to 0, here it should be the equal to sign up to capital N minus 1. So here we have the double summation, first of all for small n is equal to 0 to capital N minus 1 as it is, and then from the first equation for the discrete time representation here, in place of x of n we can have the substitution of Ck in multiplication to this complex exponential, and then the summation operation from the previous equation here. Now if we perform the summation over the small n, first of all, into the right hand side of the above equation, so that time we obtain it to the form where we have the summation small n is equal to 0 to capital N minus 1 e to the power j times 2 pi in the bracket small k minus l in multiplication to small n divided by capital N. So it obtains the value capital N. The condition that small k minus l holds the values 0 plus minus capital N plus minus capital twice n and so on in the same manner. Otherwise it holds the value 0. Now here we have made the use of the second equation to have this particular representation. So therefore right hand side of the above equation, the previous one, it reduces to the capital N multiplied to the representation of small c suffix small l. So from this, if we shift capital N to the right hand side, we obtain small c suffix small l is equal to 1 upon capital N summation n is equal to 0 to capital N minus 1 x of n multiplied to e to the power minus j 2 pi l n by capital N, where small l is equal to 0, 1, 2 up to capital N minus 1. So this is the desired expression for the Fourier coefficients that we can substitute to the first equation. So here we have the reversal way, that CL is here in terms of x of n, whereas into the first equation x of n was expressed in terms of the exponential here. So from this understanding we can have the two equations. Those are very important concerning the discrete time periodic signals here for the frequency analysis purpose. So the first equation is nothing but this equation where we synthesize x of n, the discrete time periodic signal that has been synthesized by the use of Ck along with the complex exponentials here. So here we have the summation carried out for the multiplication of Ck with that of the exponential representation here. Hence we write x of n is equal to the summation k is equal to 0 to capital N minus 1 for Ck into e to the power j 2 pi k small n by capital N here, and the reverse way that we have just now seen here. So in general we treat it to be the analysis equation form here, where we have the computation of small c suffix k to be equal to 1 upon capital N, the summation n is equal to 0 to capital N minus 1 over x of n multiplied to the exponential e to the power minus j 2 pi small k small n divided by capital N here. So the earlier equation that just now we have represented here, that it is the synthesis equation, can also be sometimes referred to as the discrete time Fourier series, that we can operate, that we can abbreviate as DTFS here. So now the Fourier coefficients in general, c suffix k, where k holds the values 0, 1, 2 up to capital N minus 1, here provide the description of the information contained into the signal x of n into the frequency domain type here. Here the Ck represents the amplitude and the phase values associated with the frequency component. The frequency component represented Sk of n, computed as e to the power j times 2 pi k small n divided by capital N here. We can also represent it to the form e to the power j times w suffix k and having the multiplication with that of small n here. Now we can have the functions as represented onto the left hand side, s suffix k of n here in the above equation to be the periodic with the time period capital N as utilized in this particular representation here. So as we have the periodicity here, the Fourier transformation, the Fourier series representation also satisfy the periodicity condition, and hence we can express c suffix k plus n is equal to 1 upon n, the summation small n is equal to 0 to capital N minus 1 over x of n multiplied to the e to the power minus j 2 pi in the bracket k plus capital N. Bracket is completed and it is multiplied to small n divided by n here. The new form is 1 upon n as it is, the summation also as it is for n is equal to 0 to capital N minus 1. X of n is multiplied by, here we have e to the power minus j 2 pi k small n divided by capital N here. So this we can represent it to be the ck, and this satisfies the periodicity condition into the simplest representation. So c suffix k plus capital N is nothing but c suffix k here. So let us conclude our topic Fourier series as we have discussed for both of the cases of the continuous time and the discrete time periodic signals here.